Didn't realize they had a Red Bull wind tunnel aerobatic team. I guess that's kind of curious. But I guess you can do these things in Vegas, can you? I've never been to the new Vegas, where it's supposed to be a fun-filled family destination these days instead of a rather seedy gambling mecca as it was 30 years ago. I guess last time I was there probably was the early 2000s, 2004 or something. I guess it was already family-oriented by those times. That's kind of curious. So a different take on wind tunnels, I suppose.
I'm just American.
Just music. Prague. Okay, I guess it's not Vegas. Interesting thing to have in Prague. I guess you can train to be a skydiver when you do that. Morning. I guess the previous version of this was unavailable, so I replaced it this morning, so didn't really check it, but very interesting for that. It's just music. It's kind of interesting that for these wind tunnels that they actually have it running. I guess you'd expect some different aerodynamic features from the wheels if they're turning or not turning, just because they have some kind of spokes in them that must do something to the airflow. But I guess you can measure the forces, the weight, and the change in weight if there is any lift from load sensors in the base. I don't know whether you can actually get any measure of the drag if it's running, because I guess the drag would be, you'd have to measure some longitudinal force. Maybe that's what that anchor is, I've no idea. That's measuring some kind of displacement that's being put on it due to the air flowing over the top. And so that's kind of curious. So if you can measure both longitudinal drag and also lift or negative lift, if it's being pushed down on the ground, then I guess you can use that to design the car to be a performance car, or you could design it for minimum wind resistance if you want fuel efficiency. And I don't know why they're stopping it, but maybe they'll tell us. Not very interesting music. Are they taking it out or are they taking it in? Looks like they're putting it in. Perhaps not. Perhaps that's an elevator to get it out of the building. I have no idea. So, anyway, and then the final one, all related to what we're talking about in terms of dimensional analysis.
Balls or any balls for that matter.
You might not be able to hear this, but
Aerodynamics basically is the study of fluid flow around objects. NASA is not in the business of designing soccer balls or any balls for that matter, or testing them. What we do use sports balls here, especially in our lab, is for educational purposes. We found that it's very easy to get young kids interested in our field by showing something they can relate to. What we have here is a wind tunnel, which is basically a chamber through which air flows. When it comes to soccer balls, what we're looking at is the flight of the ball through the air. There's a very thin
Brazil,
film
or is that
or layer
South
that
Africa?
forms near the ball surface, and it's the behavior of that layer, which we call a boundary layer, which is critical to the performance of the ball. As far as the aerodynamics go,
Brazil.
it's the structure of the outside, the material, the roughness. That's what determines the aerodynamics of the ball. Knuckling is when the ball flies erratically through the air, or it may change directions as it's flying through the air. What's been done to the bazooka is that by using these panels with fingers on it, the seam length has been increased compared to the ball in 2010. What we're looking at with the smoke patterns is where does that smoke leave the ball, at what point along the surface. And when that position of that separation location changes suddenly, then that is the speed at which the ball will knuckle the most. I think the basic message for the players is that I think you'll see less of this knuckling.
So I guess, yeah, so we're talking about dimensional analysis, and it's a technique that we can use that helps us guide experiments that we might want to run. And so these three things that we looked at, we can go back since we have some time. We got the Red Bull acrobatics team flying vertically in the vertical wind tunnel. I guess just as I presume they could use it for training people to go to do skydiving. I imagine that's what perhaps it's for, but obviously in this it's for recreation as well. And you get the idea. You can almost do synchronized swimming, right? It's almost synchronized air tunnel work in terms of being able to move around these. Quite elegant in some respects. But of course that's it's just using one of the tools that we might talk about in terms of what we're interested in, and that is a wind tunnel, which is just a way to get fluid, air in this particular case, moving at some reasonable velocity. The second one was the car, looking at getting a car running within a wind tunnel. Again, wind tunnels are big enough that you can get a full-size prototype in there, so you don't have to worry about it being a model and having to scale based on that. But you can use the same principles that we've kind of advanced last time. That is that there are two important numbers that we have to look at. One is the Reynolds number to make sure that it's kinematically the right flow regime. And at that given Reynolds number, for a car, that would be for the air velocity going at 100 miles an hour, or whatever it is you want to judge the performance at, and then using measurements of lift and drag on the weight of the car in there, and horizontal translation, which I presume might be this, little doodad here, that's measuring lateral translation, horizontal force, and then you can scale that to be able to look at the magnitudes of lift and drag. In fact, you wouldn't need to scale it in this particular case, because you're using a one-to-one model, and you're using the same velocities for the flow regimes on that one-to-one model. And so that's that. And then also for the case of the soccer ball, which is again a one-to-one model, and you saw, if we look at, I guess, some of the photographs here, again, you could look at
along the surface and when
characteristics of that flow. And you could, for instance, elevate the flow velocity and look at the different flow patterns that you see from the streak lines that result from those, from the smoke trails that you get around it. And so if you start off with a very low flow velocity, representing a ball going quite slowly through the air, you'd see the pattern that we talked about last time, that it starts off at the front, stagnation point, goes around to the back, touches again on the back, and then just departs. And as you get faster and faster velocities, then there's this wake behind it in the zone that's really the whole area of the football that has vortices in it. And that's when you get different flow regimes occurring. And so we haven't talked about it yet, but one of the classic ideas for golf balls is that golf balls are dimpled because the dimpling allows you to generate turbulent flow around the contour of the ball earlier in the flight at lower velocities, and that dimpling that generates turbulent flow makes it much more efficient in going through the air, and so it can go further because there's less force imparted by the air flowing around it, or it flowing through the air, because it goes into this regime, turbulent regime, much earlier and at a lower flow velocity. So it can go further. So there's a whole art to this. So that's kind of a classic thing. And, you know, other things like how you get curved baseballs by spinning it, and exactly is all related to the kinds of things that we'll talk about today. So that's kind of where we are. And so I'll just follow on perhaps really from where we are last time and kind of give a recap perhaps on what we talked about. And you might remember that we talked about the fact that we had two important numbers for most of the things that we'll deal with in this class, and particularly when we talk about dimensional analysis. And those were these two numbers, Euler number and Reynolds number. And you know, a very simple example is that if you took an airplane in a wind tunnel, and that airplane had some kind of wingspan across it. So we call them model and prototype. So prototype being shorthand for the full size feature. Then they don't necessarily have to be the same size, but they should be similar in the proportions. And so I guess we could write the length of the model and the length of the prototype of the wingspan. I guess we could do the width of the prototype and the width of the wings airfoil, because that would be an important dimension for us of the model. We could perhaps have a pressure on the model and the pressure on the prototype. And yeah, I don't know what else that we want to be able to consider. And we said there are three requirements that we have for similitude. It's pretty straightforward. And that's what did I say? Let's take this as equal to, say, 1 meter. Let's take this as equal to 10 meters. And so the first one was geometric similitude. And we said that the ratio of the lengths should be constant. So we said Lm over Lp equals constant, but for all the components. So in this case, I guess it would be that Lm over Wm is equal to L of the prototype over the width of the prototype. So the ratios. So in other words, if this is 1 meter and this is 0.2 meters, then this would be equal to 2 meters. So just saying that it has to look physically the same. And so it has to be geometrically a scale model of what you're dealing with. The second one was kinematic similitude. And we explained that this was really that the flow regime around it, if you took a snapshot of it, should look the same for the model and the prototype. And so this separation, well, you could imagine this is a soccer ball, and this is the separation on the backside that comes out the area of the cross-sectional area of the soccer ball. We want to make sure that the flow regime is the same. And we make sure the flow regime is the same by making sure that the Reynolds numbers are the same. So this is that the Reynolds number for the model is equal to the Reynolds number for the prototype. And the Reynolds number was inertia to viscous forces. And so that is, we didn't define it here, but we have a velocity in the model. And what am I going to choose for velocity in the model? 100 meters a second. And choose a velocity in the prototype. Let's see. So velocity times density times a length divided by viscosity. And this would be for the model, and for the model is equal to the velocity of the prototype, the density of the fluid in the prototype, the length of the prototype divided by the viscosity of the prototype. If you're using a wind tunnel for both of them, then by definition the densities of the fluids will be the same, the viscosities of the fluids will be the same. And so we just want to be able to look at, well, from this, it's going to be the velocity in the model is going to be equal to the velocity in the full-scale prototype times the ratio of the lengths. And so this would be 10 over 1. And so if we have a velocity of the prototype of 10 meters a second, so I should use some different colors. Then the velocity in the model has to be 100 meters a second to be the same flow regime. And the third one was dynamic similitude. And that is that the Euler numbers for the model and the Euler number for the prototype have to be the same. And the Euler number is a pressure. It's the ratio of pressure to inertial forces. Rho v squared equals pressure over rho v squared. This is the pressure in the model. This is the velocity in the model, prototype and prototype. If again we choose the same fluid that's flowing past it for the two, then we end up with what we want out of this, I suppose, is the pressure in the prototype. The pressure in the prototype is equal to the pressure in the model multiplied by velocity of the prototype squared over the velocity of the model squared, which is going to be, this is what we'd measure. And the velocity of the prototype, what do we say? To maintain kinematic similitude, we said that VP was 10 meters. So this is 10 squared over 100 squared. And so the pressure in the prototype is going to be equal to what we measure in the model test multiplied by 10 to the minus 2, which would be a pressure. And if we want to convert that to a force, force is equal to pressure prototype times an area. So you want to know whether you can lift up 10 tons in a plane. Typically we want a force, so we want to take a pressure multiplied by the area. The area would be the actual dimensions of it, say length times width in this particular case. So this would be kind of equivalent to pressure in the prototype times length in the prototype times width of the prototype, roughly. Approximately, I suppose, right? And so that's it. So this is 10 to the minus 2, which is this term here. And so what we've done is we've had a scale model. We've made sure the flow regime around it is exactly the same as we'd expect to see in the real case. So the Reynolds numbers in the two systems are the same. If the Reynolds numbers are the same, then the velocity that we're traveling at in our plane, we replicate in the wind tunnel by choosing the model velocity to be equivalent to that from the standpoint of matching the Reynolds numbers. And if we use that Reynolds number in the lab, then we use that to convert it to be able to get the ratio of the pressures that we act in the system. And so if we measure the pressure on the model, we wouldn't measure pressure, we'd measure a force, an uplift force typically, and then we can use that to calculate what the uplift force would be on the full scale thing. That's really all it is. And so what you can think about it is that what we're doing is we're having a Reynolds number, we're measuring an Euler number, and we're getting some relationship that matches them. We know that if we use the correct Reynolds number, then we're able to calculate from that what the appropriate pressure Euler number is that represents the pressure. So if we do both the model and the prototype at the same Reynolds number, we're guaranteed that the Euler number that we get would be equivalent, but just the dimensions, relative dimensions of the system would be different. And so that's really all we're attempting to do. So that's kind of what we're really doing in this week 9 kind of stuff. There's the 3 requirements that we have to match. Scale models, geometrically it looks similar to what the system is by being scaled down in every dimension, or if it's 1-to-1 scale, then it doesn't matter. If we make sure that the flow regime around it is the same in both model and prototype, we can define the appropriate velocity to do the model experiment at. If we do the model experiment at that velocity, we can measure the pressure in the model, and then we can convert that into what the real pressure on the prototype is. So that's it. So that's kind of where we're going with this. So we made this kind of supposition that that we can link these 2 important variables. There's a third one. We said that this is for free surface flows, so we're not so interested in this for the things that we'll do. These are for pipe flows that we'll deal with. And so what we could do is we could perhaps go back and look at some of the things that we've already talked about. And that is that we've already talked a little bit about flows around, and we'll come back to this diagram here, but look a little bit different, is that we would like to walk before we can run. And so what we could do is we could try looking at flows on structures that perhaps are more useful to us, or perhaps more germane. So we talked about pipe flow. And we've talked about changes in pressure that drive flow. We've talked about lengths, which I'll call L. We'll talk about the velocity that we get out of this, which we can call V or V bar, I guess. What else? We can define a geometry of this, which is a diameter. And I suppose we could define some other terms. We can define density of the fluid. We can define viscosity of the fluid. And we've already defined the diameter, but these are the parameters. And our interest in doing this is that if we think about it, the essence of what we talked about in terms of pressure losses in the system, we said that if it's Bernoulli's equation, because the cross-sectional area here is the same as this, there should be no pressure loss in driving this flow unless there are viscous losses occasioned along the length of it due to this kind of shear stress. And so the essence of so-called internal flows that we looked at are kind of this diagram. And just to show that it's not so dissimilar to other systems that we could look at, is we could look at maybe the case of not a tube, but something that has a closed-off end. And if we had a closed-off end, I suppose the flow would be a bit like this. But this would actually have a lot of the characteristics that we're thinking of, and that would be that it would have a pressure drop that would occur over the length of this thing. It would have maybe a diameter, which is the same. And I've kind of spoilt it by drawing this here, but you could imagine that the viscous forces on this would not be on the inside of this cylinder because there's no flow in here. So I'm thinking about this being stubbed off, so the flow has to go around it. Then this is exactly the same behavior, kind of, but this is what we'd call an external flow. And it's not so different from an airplane, not a very efficient airplane. You could imagine it being an airfoil. But it's essentially the same behavior that we're dealing with. Except now that the shear stress that we're dealing with is now on the outside of this. And you could think of this as being the drag. This is why a car doesn't go as fast as you want it to, because if it's a Honda, whatever those square-shaped Honda utility vans are, it's broad into the air and it's got a lot of wind resistance, as opposed to something which is a bit more aerodynamically efficient. And so the reason for looking at this is that if you remember from 8.3, our last period together on Friday, that we came up with an expression which was this. I'll go back to it in a second. So write that, try and remember it. We'll come back to it, and I'll just switch back to 8.3. If you remember what we talked about these Navier-Stokes equations and how we could solve these three equations and continuity equations for some very simple geometries. And the very simple geometries that we talked about were for flow through a parallel-sided duct, like this, or flow along a tube. And if we had flow along a tube, we had this expression that comes out from basically throwing almost all the terms of those four equations away and just dealing with the ones that we needed to. And we ended up with a very simple expression for laminar flow. And so all I'm doing is repeating this, where 2 times the radius is the diameter that we dealt with before. Wish I could zoom straight through to the same location. Don't want to be scribbling on this. Am I already past it? No, that's the last one. You can cut this out. So this is the expression here. So what we could do with this is we could write this out, and we could, well, I'm going to write it out. Well, I guess I don't have to write it out. I could do something to it. What do I want to do? I want to multiply by velocity. So this is the average velocity coming out here. I want to multiply by density on both sides. And I want to divide through both sides by dp. And so now if I get rid of some terms, I get rid of, let's use something that's colorful. Pressure I get rid of. I could gather some terms. So immediately you see that this value on the left-hand side is, no, not that, is 1 over an Euler number. So an Euler number is pressure divided by density times velocity squared. So pressure divided by density velocity squared is 1 over this. And I could multiply this term and d. And then I have d over dx. So this remaining term and this remaining term. I have 1 over 32, and I have an average velocity, a density, a characteristic dimension, and a viscosity that's left here. And so this term here is Reynolds number. And so immediately, just by taking this laminar flow equation, so laminar means there's no kind of separation of vortices behind the soccer ball as we saw before. It's just an enveloping flow that's kind of creeping around it. Then we can define this behavior. And so essentially from this expression, we have something which is 1 over an Euler number is equal to a dimensionless term. This is length over length. This is 1 over 32. And this is a Reynolds number. And so physically, this means that I could draw a graph for flow, which happens to be for flow along this pipe, but it's also a very similar equation for this. It's just an external flow. And that would look like 1 over EU is equal to some function of Reynolds number. And so this is a finite number. This is 1 over 32. And so I don't know what it would look like, but it would look like this. As you increase Reynolds number, you'd expect to increase 1 over Euler number. So it would look like this. Increasing velocity, you'd expect this to go up as well. But we could also write it as the reciprocal of that. So we could take 1 over, and that would be equal to dx over d, 32 over Reynolds number. And then if we plotted that, we would get Euler number, which is, in our definition, what is it? It's pressure divided by density times v squared. And we have Reynolds number, which is equal to velocity, density of the fluid, some characteristic dimension, which is most usefully the diameter of our pipe. Could be the length, but it's most usefully the diameter, divided by viscosity. And if we do that, this equation should look like this. The opposite gradient from this. And if we do that, it's useful for us to do that. It turns out that this Euler number, if we wanted to look at it, we can also write as something called Euler number is proportional to friction factor. Which we'll call a squiggly f, which says something about the resistance to flow along a pipe, which we'll use. In fact, we'll discover that the head loss in our Bernoulli equation is equal to the length over diameter ratio of our pipe multiplied by a friction factor times v squared over 2g. Dynamic velocity change, a drag coefficient you can think of, and how long the pipe is relative to its diameter. And so what we'll develop is some charts that look exactly like this. We said already that this is for laminar flow. So this means that if we think of it not as flow within a pipe, which is not so easy to understand, we kind of drew these pictures last time. If you think about it as flow around a sphere, then laminar flow would be happily along here, hugging the contour and separating off the back. Just hugging the contour. And this would be a magnitude of a Reynolds number of about 2,000. And as we go beyond this number here, we find out, I won't do it in blue, I wanted to change colors, that then it becomes horizontal. We'll find out that there are a whole series of lines, and these lines, well, probably not information we need right now, are proportional to epsilon over d. And so if you think of your tube as being a tube that looks like this, of some diameter, then epsilon is just the roughness of the wall, the amplitude. So if you do top and bottom, this height here is epsilon. So as you change the roughness of the wall, then you get different numbers. It doesn't really matter what the roughness of the wall is if it's laminar, but as you go into the second regime above a Reynolds number of 2000, then this is turbulent. And so turbulent means, in terms of thinking about flow around a sphere or a golf ball, for instance, which is perhaps a bit more easy to visualize, is that now this flow looks like this. It hits it, goes around it, but then it comes off the backside with these vortices that are here. So laminar flow, turbulent flow, they have different characteristics, and this is why we need to index our behavior relative to the Reynolds number. At a low Reynolds number, you get these creeping flows, and actually it turns out that the frictional losses are proportional to the viscosity, because it's this drag on the cylinder that is causing this. And actually, as we get to be turbulent, the frictional losses are proportional to density of the fluid and the velocity, v squared over 2g. And you can imagine that, you know, when we did the San Francisco International 747 versus the truck, the whole idea was that fluid comes out of here at some velocity, it stagnates on the truck, it transfers the velocity from the jet engine into a pressure on the truck by stagnation, and this is what pushes it over. So this is in, we never said at the time, but this is in a turbulent regime where we can make that change. In this particular case, the transfer of flow velocity from the energy onto this is merely by the drag, by the shear force on the sides of this ball. This is because it's hitting it face on, and it gets it in the chest, and it's pushing it backwards. This is because all the air is flowing around it and pulling it by the drag that the viscosity acts on it. So perhaps we don't have to understand anything more than that. But the reason for introducing this here and introducing it in this kind of vein is that we'll understand this, and perhaps it's worthwhile drawing. We're almost out of week 9. In week 10, we'll talk about pipe flow. And so this is in weeks 10 and 11. And that's exactly what we're doing. We're talking about a friction factor, and we're looking at flow along a tube. I guess we've kind of done a couple of these, but never hurts to reinforce these ideas. And we end up with a figure which gives us a friction factor as a function of Reynolds number. We know what those terms are. We know that this is a number that's about 2000. We know that this value for laminar flow, actually for flow in a pipe, is equal to 64 over Reynolds number. We kind of know some of that here, right? We have 32 over Reynolds number. It's a factor of 2 out, probably because we define friction factor a little bit differently as a 2 times Euler number, maybe. I can't remember. And so this is exactly the system we get for that. between laminar, stopped, and turbulent. If we look, as we will do, at what we'll call external flows, flows around wind turbine blades and flows around airfoils, then we have exactly the other figure that we kind of drew, and that is that flow goes around it. And I suppose for this one, what did we say? That the head loss is equal to length over diameter friction coefficient times v squared over 2g. So this would be the average flow. And this is the length of pipe. So this is the term that goes into the Bernoulli equation. For external flows, we'll have a coefficient of drag, which is equal to uppercase a curly drag force. So I'm sorry to use the same symbol, but if you imagine a force acting backwards, which is a curly D, over half rho v squared times a. So remember from this, a half rho v squared is part of our Euler term. So you could think of this being equal to a pressure. And so this is kind of equal to a pressure. And a pressure times an area gives you a force. And so A area for here would be the cross-sectional area of this system. And no great surprise, we could draw a graph which looks like this. Reynolds number, coefficient of drag, this term here. Actually, it'll look, you'll see why we do this later. Again, laminar and turbulent. Can't remember exactly what this breakpoint is. It's of the order of 2000, something like this. And so this allows us, for instance, to be able to calculate the drag force on something, or it could also be a coefficient of lift. If I drew, it's almost a coefficient of lift is equal to a curly L divided by half density of the fluid, velocity of the far field velocity of the fluid, v squared times a. And so this could also be coefficient of lift. Same idea. And so all I'm trying to make the point is that these curves look the same. This happens to be an internal flow. This happens to be an external flow, but it's really the same process. Here, there's a force exerted on the side of the pipe on the fluid, and we're interested in that force exerted on the fluid because that slows it down. That's what the head loss is. Here, there's an external force on the closed pipe that we're interested in actually the magnitude of that force itself, not its influence on the fluid, but on the influence on the body as to whether it gives drag for the car, pulling it down the road, or whether it gives lift or pushes down the car. And I guess just to close off the three sequences, we'll also talk about open channel flows. And that would be in week 13. And the idea is that we can have something that looks like my drawing is any good. You get the picture. This is flowing again at some average velocity. And we would have a characteristic dimension on this, which would be probably, well, we have two characteristic dimensions. We would have, actually, let's do, yeah, two characteristic dimensions. There's a height of flow, and there would be a width of flow, but let's not worry too much about that. I guess this would be a D. And we'd have another curve which would look like this. And it would be Reynolds number. It would be what we call N. N equals a Manning coefficient named after someone. Again, we have this transition from laminar to turbulent. Again, we'd have a figure that looks a bit like this. With a whole bunch of these. And we'd find that when we looked at this, these flows, because D is large and Reynolds number is equal to density, average velocity, some characteristic dimension times viscosity. If this is large, then RE is large. And so we'd find out in this particular case that we always exist somewhere here. We always exist east of this transition. And so we're always in this turbulent regime, and this would represent a ditch that's smooth. I can't remember which way it goes up. This would be a ditch with grass in it. So different amounts of drag on the ditch are given by the different characteristics of the walls of our flow regime. But the important thing, I think, for all of these is to realize that these are just variations on a theme for these particular conditions. And they all form from this idea that we can define behavior in terms of understanding these two important non-dimensional variables. Three, I suppose, that the model, if we're doing a model, looks the same no matter what its scale. And if we want to be able to calculate what the pressures or the drag on a system are, then we need to make sure that we're flowing in the same geometry regime. It looks the same if we take a snapshot. If we took a snapshot of the model or the prototype and could look at the flow around it, they'd look identical to each other. They'd be self-similar. And if that's the case, we're traveling at the same Reynolds numbers. And if that's the case, then we can also use the similitude that's due to the Euler numbers. So that's kind of this little page here, I guess, is quite important for the things that we want to do. Okay? So I don't know whether we want to do it. Maybe make a start on it. Questions? No? Incredibly powerful technique. All right. Won't wait too long for questions. Taking pictures of it? You're welcome to take a picture. You can always take a screen capture off YouTube. So we started out by saying that dimensional analysis is kind of a misnomer because it's really, we work in non-dimensional numbers. Reynolds number that indexes flow, and Euler number which indexes the forces that are on a body. We also said that we have this fancy theorem called Buckingham Pi, named after Mr. Buckingham, who is a fluid mechanicist. And Buckingham Pi is a formal method to be able to define exactly what parameters control your particular system that you're interested in, and to come up and decide whether these are really the parameters that we need to use or whether there are some others that we need to worry about. And we kind of alluded to it before, because you remember that when we started out last time, I made the case that we looked at something called Darcy's law. We could define the individual parameters which control flow within a sand pack, and we could do something with those variables to be able to come with a formal way to divide them into non-dimensional variables. And we could, with these 4 different variables represented by 2 different conditions, mass, length, and time. None of these relate to mass, but they do relate to length and time. Then 4 variables minus 2 coefficients give us 2 potential non-dimensional variables. So if we want to group these, we could do it just by inspection. The only way that we could group these together in a minimum set is to link the 2 ones that have velocities together by dividing one by another, velocity over hydraulic conductivity, and by linking the head drop along the length of the flow, dividing those by each other, and we ended up with 2 parameters. And so we could link those 2 in the same way as what we've just done. We've said that we could use Reynolds number and we could use Euler number to be able to develop a relationship so that we could define a relationship that we could move between different scales, do things on a model, and then define what the behavior is on a larger scale. So we can use this same formalism that we kind of jumped into last time in a bit more sophisticated way, as in Buckingham Pi Theorem. And you'll see it here. So all I'm going to do is try and explain it, and you can read this just as easily as I can say it. And so it says, if an equation involving k variables, so length of the pipe, diameter of the pipe, so this would be length, this would be diameter, this would be viscosity, this would be density, blah, blah, blah. If it can be reduced to, if it has R reference dimensions, so R would be mass, length, and time. Could also be temperature. We said there was a 4th one, but we won't use that here. Then K minus R gives you the total number of non-dimensional parameters that will define your system. And so what we might do is we might try doing it for exactly the system that we've looked at. And the system that we've looked at, if we make a start on it, would be for our pipe. And so our pipe would be this. It would be a velocity. It would be a density. It would be a viscosity. This is going to be a diameter. Bad choice there. And this parameter here, delta PL, is dP over the length. So yeah. So this would be a pressure drop. And it would occur along some length, dl. So all we're doing here is we're combining these 2 together to get one parameter, which we think is appropriate. And so then we have 1, 2, 3, 4, 5 parameters. Velocity is length over time. Mass, density is mass per unit length. So we have density is mass per unit volume, and velocity is length per unit time. So we have all of these three represented. And so we think that for this system, we're going to have a total number of phi minus 2 parameters, which is 2. Don't want to give a game away, but we could guess what those parameters might be. But let's see how we formally get those. So we list our variables: diameter, viscosity, density. This would be rho g, and pressure drop. If we define density, then we probably don't want to define unit weight because it's included in it. So we have to be a bit skillful about what we do. So ignore this number 1 because we're going to use these 5 terms that we have here. These will be our 5 terms. Don't care about this. Well, we do. We want to define each of the variables in the dimension. So units of density are kilograms per meter cubed, which is mass per length cubed, which is ml minus 3, right? Probably not the best choice of color. And then I'm going to, well, I guess I don't think you need the wording for this. So this is the deal. So you have these in your notes. So we're going to try and use Buckingham Pi to do this. We've got 1 minute to go, so I probably won't even start. We can do it more leisurely next time. All we'll do is we'll define some parameters in this. We'll define some parameters that are repeating, and the repeating ones will be ones that mention length, mass, and time. So all of the dimensions are included. So if we choose diameter, velocity, and density, we take diameter, velocity, and density. And these will be our repeating variables. And then we will choose first a non-repeating variable, which is pressure, and do something with it. And then we'll choose our second non-repeating variable, which is viscosity, and we'll do something with it. And for each of those steps of doing something with it, we'll come up with a non-dimensional term. And the whole idea is that we will classify each of these variables in terms of these basic units, mass, length, or time. And we'll combine them in some way by taking the repeating variables, multiplying it by each of the other dependent variables individually. So this is one independent variable, this is the other one. And all we want to do is we want this group to have no dimensions of mass, length, and time. So the exponents of these must be 0. And so if you think about defining the variables that represent pressure gradient, is this. The variable that represents diameter is just length to the power a, velocity to the power b, and density, mass over volumetric volume, to the power c. We want to figure out what these exponents are, such that when we multiply this equation out, the units of this term have no units. And if by definition our choice of A, B, and C give us a term with no units, then this will be one of our dimensionless variables. And my guess is that since this has pressure in it, this first one will probably be equivalent to an Euler number, which is pressure over rho v squared. I'm guessing. Yeah. Remember that this PL is, I'll go through this again next time. this PL is actually DL of this. So this is actually dP over V squared rho times D over DL. So this is also dimensionless, but this certainly is a non-dimensional group, which is an Euler number. So that's what we're going to do. So let's not spoil our fun for next time. We'll start from the scratch. It's an incredibly important and powerful technique. It's always a question on the third test, and it's a recipe. Once you know how to do the recipe, you've got it. It's absolutely straightforward. But the idea is that we want to have a formal method of being able to take the parameters that describe our system and divide them up into non-dimensional variables. And it's no surprise that the non-dimensional variables that we'll get for this case of flow in a pipe will be exactly the same non-dimensional variables that we've already said that control the flow, because we've gone through it for this very simple case. But of course, the closed form solution that we've used to get the relationship between Euler number and Reynolds number for a pipe is only valid in this region. We don't know what it looks like over here at all. And so to get this information here, we have to do experiments where we'll increase the flow so that it becomes turbulent in the pipe, and then we can get the right relationships experimentally to be able to define exactly what these relationships are. So we'll do that next time. Okay? Great. Questions?